This is my video number 14. I will still talk on limit of a sequence. Yeah, say limit of the sequence. Limit of the sequence. Continue. Now, for this video, we begin with the theorem. I'm going to prove this theorem. If a sequence un converge, yeah, is a positive real number sequence converge, then un is bounded. Un is bounded. So what do we understand from this theorem? First thing is that given un converge, what does it mean un converge? Converge means the limit exists, so which means the limit un n approaches infinity, let's say converge to some number L, then bounded. What do we mean by un is bounded? Bounded means if we take the absolute of un, this will always less than some number n. So this means bounded for all n, for a bigger n. So what we want to show here is that if we were given the our sequence converge, which means satisfy that condition, then it must bounded. This means the absolute of un must less than some number n, m. Okay, so from this definition, this definition says what? Given any epsilon positive, all right, we can find n positive such that the difference between un and L always less than epsilon for all n greater than n. This is the definition of the limit of the sequence. Okay, we can use this because we know that, or we were given that un converge, so we can use this statement. Now let's say there exists such n that capital that is bigger than n then the limit of the sequence exists. So from there we can write un less than L less than epsilon for all n greater than n. Okay, the reason why, because un converge, so we can do that. And from that inequality you can take off the absolute symbol there. So what we have now, this is less than epsilon greater than minus epsilon. Okay, that's true. And then you can bring out the L to the left and to the left and right. So we have un less than L plus epsilon greater than L minus epsilon. Okay, so if you look at this, if you take the right hand side, so we have no problem with this, and if we take the left hand side, L is some numbers, you put negative to it, it's getting smaller than, less than that. This inequality is true. So why do we do this? Because we want to show, we want to take the absolute of un. Okay, we want to take the absolute of un. Now, so from there, so we have minus, so this is of course on the left side here, on the left hand side. So we have, this is negative of L plus epsilon. That's correct, right? So if you look at this on left hand side and you look at the right hand side there, so what we have un less than L plus epsilon for all n greater than n. So what does this mean? So it means that if you have a sequence, so this is our L plus epsilon somewhere there. This is L plus epsilon. So you can see from here, none of the terms, element of the sequence bigger than L plus epsilon. So which means that for some n greater than capital N, this inequality satisfies. And on the other hand, if you look at this kind of sequence, for example, this kind of sequence, let's say we have, this is our n, okay, so we can see for n less than n, there is some terms that bigger than L plus epsilon, bigger than L plus epsilon. So we need to determine this as well. Okay, we need to determine. So therefore, we let m, some number m, maximum between all those things, L u1, because this is smaller than, so u1, u3, u2, u3, and so u1, u2, and so on, up to some um, okay, up to un, and plus L epsilon for that case, L over epsilon. If we can show that, or you can find some n, you pick up m bigger than all this number, you take the biggest one. For this case, of course, this is the biggest one. For this case, this is the biggest one. Okay, for this case, this is the biggest. For this case, this is the biggest. We pick up all those biggest numbers, so definitely we have un less than that number m. Okay, so it shows that, so therefore we can say this un bounded. Okay, all right, now what about the converse of this? Converse means if un bounded, does that means the limit or the sequence converge? Or I can write un converge to some number, u, say, for example. I put a question here. Okay, the above statement is true. We have proved that they are true. What about the inverse of that? If bounded, does it converge? Now for this, we look at the example. So let's say I have this kind of sequence, un, let's say minus 1 n. Okay, so for this sequence, so if you list down the element of that sequence, so we have minus 1, 1, minus 1, 1, minus 1, and so on, and so on. So what we can see in this case, so our sequence look like negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1, negative 1. So this sequence does not converge to a specific value. Instead, it just what we call that, oscillates between two values, minus 1 and 1, minus 1 and 1. It's not going beyond than that, or lower than that, or smaller than that, and as well as it doesn't converge to a certain value. So in this case, it's bounded but not converged. All right, it's converged but not bounded. So it means that this statement is not true. Okay, this statement is not true. You can choose you can choose many examples. As other example, if you consider, let's say we have this example, cos n pi over 2. Okay, so this kind of sequence also having these properties, which means it's bounded. We can show this sequence is bounded. It's not difficult. This is less than 1. If you take the absolute of that, this is less than 1. Okay, so which means it is bounded, but this sequence is not converged. Okay, so we have done that. Now I hope you understand this thing, the concept of convergence and concept of boundedness. Okay, so let me recap those things. We have this sequence, okay. Let's say this sequence converges to some number u, means un bounded, but the converse is not true. Okay, the converse is not true. Now let's look at some other definition. We say a sequence, un that increasing if you have if the sequence increasing, you look at the increasing sequence. This is increasing sequence. Okay, this is increasing sequence. In this case, it's converged. In this case, diverge, but both are increasing sequence. Okay, now un is increasing sequence, increasing if we have u1 less than u2 less than u3 less than so on, less than un less than un plus 1 and so on. Yeah, look at this. This is increasing sequence. This is u1, 1 is here. This is u1, this is u2, this is u3. So we can see from there, u2 is always bigger than u1, u3 bigger than u2, and so on and so forth. So it means that the sequence increase. Okay, the number is getting bigger. So the important properties here that we need to look at is that relationship. Yeah, un is always less than un plus 1. So for this case, our sequence increase, and un we say un decreasing. Well, this is decreasing. Okay, don't bother about my handwriting. If we have u1 is greater than u2, greater than u3, and so on, greater than un, greater than un plus 1, and so on. Okay, so for the decreasing sequence, you can take the example. Just look at this sequence. Okay, whatever the sequence, but having that kind of behavior. So we can see that when n equal to 1, so we have u1 here. When n equal to 2, so we have u2 here. For n equal to 3, so we have u3 here. So we can see from this picture that u1 is bigger than u2, bigger than u3, bigger than, and so on and so forth. Okay, so again, the important part that we need to look at is that relationship. Okay, un is always greater than or equal to n plus 1. So in this case we call it the sequence decrease. And for either it is increasing, either un, I use this symbol here, increasing or decreasing, we say un, okay, we say un, I put that way, we say un is monotonic. So in the simple word, monotone means if it increase, it keep on increase. If it decrease, it keep on decrease. So we don't have kind of here like this. Okay, this we don't say this sequence monotonic sequence. Okay, monotone, because some point that is increase, other point is decrease and increase and decrease. So this is not monotone. For monotone, this is we call monotone. This is we call it monotone. This is we call it monotone. For this case, so we have monotonically increasing sequence as well as that. For this, we say monotonically decreasing sequence. I can write this here: monotonically decreasing sequence. For this case, monotonically increasing sequence. Alright, now let's see some example how to show the sequence increase or decrease. Let's say if I have our un is given as 3 over n plus 5. Okay, this is decreasing sequence. Why? Okay, look at the decreasing sequence. We have this decreasing sequence, our un greater than un plus 1. So if you can compare this, un is given as that, so our un is 3 over n plus 5. Okay, and if you increase n to n plus 1, see what happened. So we have 3 over n plus 1 plus 5, which is 3 n plus 6. Look at the denominator. We have a fraction. You increase the numerator. What happened? The numerator bigger would be less than. So overall, so we have those greater than. Un is greater than. So this is actually un plus 1. So it satisfies this relationship, right? So un greater than un plus 1. You look at here. So we have un greater than un plus 1. So therefore this sequence increasing. Okay, this sequence increasing. It's monotonically increasing. Other example, I give you another example. Let's say if I have un n plus 1. Okay, so this is increasing or decreasing sequence. So let us see. So if for decreasing sequence, so we have, remember that for decreasing sequence we have un greater than un plus 1. For increasing sequence, we have un less than un plus 1. Alright, now if you look at this, if you take un and un plus 1, let's say I want to check for the decreasing sequence. Okay, we check for the decreasing sequence. Check for decreasing sequence. Okay, I think I better write. I'll check for decreasing sequence. So if you want to check for the decreasing sequence, we choose un as that. Our un is given as n over n plus 1. Okay, so you want to show it's greater than un plus 1. This is greater than un plus 1. Our un plus 1 comes, so we have n plus 1 over n plus 1 plus 1. This is un, then un plus 1 is this one. So this is un plus 1. Okay, so look at this inequality. Look at this inequality. From there, I can solve this. n plus, this is n plus 2. So bring it to the left. We have n plus 2. This is greater than n plus 1. N plus 1 squared. Correct? So what we have here, this is n squared plus 2n greater than this is n squared plus 2n plus 1. Okay, so if you cancel, that one is cancel out, that one cancel out. So we have the left hand side left nothing, 0. 0 is greater than 1. Is this inequality correct? No, it's not correct. It's not correct. So which means our sequence n plus 1, since it is not decreasing, so it is increasing. Okay, so therefore our sequence is an increasing sequence. You can check for increasing for the increasing sequence. For example, let's check for the increasing sequence. So our un is that n plus 1. We want to check for increasing sequence. Okay, same sequence, because from there basically you can make a conclusion, but if you don't trust, you can check those things. So we have n plus 1. This is our un. Okay, for un plus 1, we have n plus 1 over n plus 1 plus 1. This is our un plus 1. We want to check for the increasing sequence. So which means the inequality, you have un less than un plus 1. If you proceed this, so here we have n plus 2 less than n plus 1 squared. It's just the same, just follow those things. So this is what you have, n squared plus 2n, n squared plus 2n plus 1. So this is cancel out, this is 2n, cancel out, so you have 0 less than 1. So this inequality is correct. Okay, this is true. So therefore our inequality here, un less than un plus 1. So therefore our un is increasing sequence. I hope you can understand those things. Give you another example so that to make it clear to you. Let's say we have un equal to n over n squared plus 1. Let's say I have this sequence. Now you want to check for the increasing sequence or decreasing sequence. We want to check it for the decreasing circle. Is decreasing. Decreasing. So which means we have un for the decreasing. Un is greater than un plus 1. We want to check for that. So take un. Our un is given as that. This is n over n squared plus 1. We want to check for the decreasing. So this is greater than un plus 1 is n plus 1 over n plus 1 squared plus 1. This is our un plus 1. So look at the inequality there. Try to solve this. So what you have n, this is n plus 1 squared plus 1 greater than n plus 1 n squared plus 1. Correct? So here we have so what do we have here? This is n squared, n cubed. So we have 2n plus 2n, so 2n squared. We have 1 plus 1, so 2. So plus 2n. There's the left hand side. Right hand side we have n cubed. We have n squared. We have n. And we have 1. Okay. You can cancel out that. What left is you can bring this to the left side. So you have n squared plus n greater than 1. So look at this inequality. Remember that our n is a number greater than 1, is a natural number. Yeah? 1, 2, 3, 4, 5, 6, 7. So since n is a natural number, so our inequality, so let's call this star, yeah? Then our star is true. Yeah, you choose n equal to 1, 1 plus 1 is 2, 2 greater than 1, so it's true. You choose any n greater than any natural number n is always greater than 1. So it means this statement is true, which imply that our inequality is true. So therefore we have un greater than un plus 1. So therefore our sequence un is decreasing. We have shown in the previous example that I showed you just now that if we choose a wrong inequality, then it will deny the logic of numbers. Okay, but in this case it's true. Logic numbers is true. Then our choice is true. So therefore this sequence is decreasing. Okay, so I think I stop there for this video. Thank you.